Thanks again.
Great. Thank you, everybody. Take care and enjoy the rest of your conference. Bye-bye.
Thank you. Bye.
Morning, everyone. The next session topic is based on hybrid deep learning architecture for human activity recognition, and it's either presented by Pillay or Anban. Are they available?
Yes.
Okay, I'll leave you to take it over.
Good morning, everyone. My topic today is on hybridized deep learning architectures for human activity recognition. So what is human activity recognition? It's the process of identifying the action and goals of individuals from a series of observations of the activities performed. Example of our applications include foul play detection in sports, abnormal activity recognition from CCTV videos, and gesture recognition for controller-free gameplay. Popular deep learning architectures of R can be placed in the following categories, such as recurrent neural network, two-stream CNNs, and 3D CNNs. Two-stream CNNs are the most popular architecture category in our research. It typically consists of a spatial and a temporal stream. The spatial stream operates on the parent sequence that describes the person's actual position relative to other objects within the video frame, whereas the temporal stream deals with motions that most often occurs when there is a change in the position of the individual related to other objects in the scene. The aim of the research was to determine a two-stream deep learning architecture to improve existing state-of-the-art classification results for action recognition of single human activity performed over a short duration using video data. The proposed architecture in the study was developed using an hybridization strategy by combining a temporal segment network, which is a two-stream CNN, and a multi-layer perceptron, which consisted of one hidden layer. So a temporal segment network was introduced to improve the performances of traditional two-stream CNNs. It performed video level predictions by using the visual information of the entire video. It also consists of a spatial and temporal stream. The input video is split into K segments of equal durations, and the network operates on these segments, and the output are fused to obtain a final classification score. So in the proposed architecture, the input video is also split into N segments. The copies of these segments are passed as inputs to the spatial and temporal stream. In the spatial stream, a random video frame is chosen from this segment and is passed as input to the spatial stream CNN model. The CNN model operates on the video frames and produce N output vectors. And these output vectors are fused using the average fusion strategy to produce a single feature representation of the spatial information of the input video. For the temporal stream, a group of 11 consecutive frames are chosen from random positions from each segment. These frames are then served as inputs to the FlowNet 2.0 optical flow algorithm to produce 10 optical flow calculations. The optical flow is a pattern of apparent motion of objects, surfaces, and edges in the visual scene caused by the relative motion between the observer and the scene. In a scene, the FlowNet 2.0 optical flow algorithm utilizes deep neural networks to produce optical flow estimations. The FlowNet 2.0 algorithm is also able to detect small motions and outperforms all other optical flow algorithms available. These 10 optical flow calculations from these segments are stacked together to form a batch input to the temporal stream CNN model. The temporal stream CNN model operates on these batch inputs and produces output vectors for each segment. These output vectors are also fused using the average fusion strategy to produce a single feature representation of the input video's temporal information. Thereafter, the spatial and temporal feature representations are fused using the weighted average fusion strategy to produce a single feature vector that serves as an input to the MLP network. The spatial and temporal weight was set to 1 and 1.5 respectively. The MLP classifier processes the input vector to produce a classification scores for each of the class labels. And then finally, the class label with the iris score value is the predicted label for the input video. So this architecture was trained and tested using the KTH human activity dataset, which consisted of 6 actions, namely the boxing, hand clapping, and waving, jogging, running, and walking activities. Each category contained approximately 100 videos. All the videos had a fixed frame rate of 25 frames per second and a low resolution of 160 by 180 pixels. The dataset was divided into 70% for training, 10% for validation, and 20% for testing. The confusion matrix was used to assess the performance of the proposed architecture. The accuracy was calculated by counting the number of times the architecture's output matches the expected output, which was thereafter divided by the total number of inputs. The formula is the same as calculating precision. The 5 different CNN models that were investigated using the spatial and temporal information are the VGG16, AlexNet, SqueezeNet, ResNet 50, and the OpResNet 50 CNN model. The OpResNet 50 CNN model is a ResNet 50 CNN model that employs the octave convolution, which was introduced by Facebook research in the recent years in an attempt to remove any redundancy that may exist in CNN models. The octave convolution have shown to increase classification performances of ResNet CNN models, and therefore it was chosen to be investigated in the study. Table 1 shows the results of each CNN model when trained using the spatial information of the KTH dataset. The VVG16 performed the best with an accuracy of 61.75%, and the OpResNet 50 model came in second and with an accuracy of 60.25%. In table 2, it shows the results obtained when training the CNN model with temporal information of the KTH dataset. Here, the OpResNet 50 model obtained the best accuracy of 78%, and the ResNet 50 came in second with an accuracy of 77.67%. The top 2 best performing CNN models on the respective spatial and temporal streams were chosen as candidate models to be further investigated. Different combination of these models were employed in a 2-stream architecture, which was a TSM model. The combination of using the OpResNet 50 CNN model for the spatial and the temporal stream produced the best accuracy of 82.5%. These CNN models were then chosen to be employed in the proposed architecture. And next, we look at the different MLP architecture to hybridize with the TSM model. The 3 different MLP architectures definitions are given in table 4. The number of input and output neuron corresponds to the number of classes of the dataset. The MLP version 1 has 3 neurons in the hidden layer, and while the MLP version 2 and 3 has 12 neurons in the hidden layer, which is twice the number of neurons that exist in the input and output layers. The version 2 and 3 differs by the activation function that was employed. In table 5, we display the results obtained by hybridizing the TSM model with various MLP architectures. All hybridizations have significantly increased the accuracy of the TSM model. However, the hybridization with the MLP version 2 stood out the best, and all these were trained for over 100 epochs, and gave us an accuracy of 96.67. But analyzing the results, we saw that there was still potential for this architecture to get a higher accuracy level. And so we trained it for 150 epochs, and we got an even higher accuracy of 97.5%. So comparing the results to state-of-the-art results on the KTH dataset, the accuracy comes in second, which was tied with the accuracy obtained by the work done by Shayo and others. Khan and others work that was produced an accuracy of 99.8, which is the current state-of-the-art results on the KTH video dataset. So evaluating the performance of the proposed architecture using the confusion matrix is given in table 7. All the videos from the best, all the videos from the test sets for the hand waving, running, and walking actions were all correctly classified. However, the remaining 3 actions each had 1 misclassification. In conclusion, the proposed architecture was developed by using by hybridizing a true temporal segment network and MLP. It was also utilized state-of-the-art methods such as the FlowNet 2.0 optical flow algorithm and convolution. The results obtained on the KTH dataset are very competitive to the existing state-of-the-art architecture performances. In future work, multi-layer perceptron with more hidden layers could be investigated, or a segmental importance strategy could also be incorporated to the architecture that assign the importance of each segment's contribution to the final classification. Thank you.
Thank you. We'll move over to the first question.